Hello, welcome to this lesson on the cathode ray oscilloscope, sometimes called a CRO, or an oscilloscope, or a scope. We can use this device as a voltmeter and to measure voltage waveforms, that means voltage time graphs. Got some other uses as well, but let's stick to these. This is a picture of a typical commercial oscilloscope. Notice the screen in the middle has a grid of horizontal and vertical lines. This means you can take readings from the screen. There's all sorts of controls and knobs and buttons and inputs on the real oscilloscope. We're going to simplify things by only looking at two of them. The controls we're interested in are the Y sensitivity and the time-based controls. These are the really important ones you need to understand. So here's a simplified oscilloscope. The grid is the screen. When the thing's on, there'll be a bright spot showing in the middle of the screen, and I've shown that as a blue blotch. Let's see how we can use this device to measure voltage first of all. Now these two little circles on the bottom left are our inputs. I'm calling them Y inputs for a reason. If we apply a voltage between these two inputs, the spot on the screen will move up or down, like on the y-axis of a graph, so we call them the Y inputs. This knob I've marked in yellow is called the Y sensitivity, and I've marked three values here, 2, 4 and 6, in units of volts per division. Now division means the space on the side of one of these squares. So if I've set the Y sensitivity to 2 volts per division, you can see the pointer is pointing at 2, it means that each vertical division corresponds to a 2 volt change. Think about that. Let's do a little problem. Here's a cell connected to the Y inputs. The Y sensitivity is set to 2 volts per division, and the spot is up here now. It was in the center. When we connected the cell, it jumped up here. The question is, what is the EMF, or if you prefer, what is the voltage from the cell? Pause the video and see if you can work out from the information on the screen what the voltage is. Well, I hope you did it. That spot has shifted from the middle up here. We say it's been deflected. The deflection is 1 division, 2 divisions, and about 0.4 divisions. 2.4 divisions. Each division is 2 volts because that's the Y sensitivity setting. So the EMF, or the voltage of the cell, is 2 volts per division times 2.4 divisions. It's 4.8 volts. We've used the voltmeter, the oscilloscope, as a voltmeter. It's a very good one. It has a very, very high input resistance. What do you think would happen if we connected the cell the other way around, with the positive side on the left and the negative on the right? Pause and have a think. The answer is the spot would have moved from the middle to the bottom by the same amount as the previous screen. 2.4 divisions down. So that's a negative voltage. Here's another question. Take a look at the setup here. The problem is this. What will happen if the Y sensitivity is changed to 4 volts per division? So it's on 2 at the moment. I turn this little yellow knob anti-clockwise so it's pointing at 4 volts per division. What do you think will happen to the spot? Again, pause the video, try and work it out for yourself. And here's what would happen. Going from 2 volts per division to 4 means the deflection will be halved. Instead of standing for 2 volts, each division represents 4 volts. We could actually work out the amount of deflection. 4.8 volts is the known voltage. It results in a deflection of 4.8 volts. We'd have to divide by the number of volts per division, and that would tell us we've got 1.2 divisions. So that spot would have moved up 1.2 divisions. Now let's look at the other control shown in red. This is called a time-based control. At the moment it's set to the off position. I've marked a couple of values on there, 5 and 10. They're in units of milliseconds per division in my example oscilloscope. Let's turn the time base on, turn it to 5. What happens is you'll see a continuous line across the screen, and that's because the time-based circuit inside the oscilloscope is making the spot move across the screen at a steady speed. When the spot reaches the right side, it moves the spot instantly back and starts it moving across the screen again, and that process is repeated over and over. Now your eye can't follow the spot if it's moving really fast, and the line appears as a continuous one rather than a moving spot. And that continuous line is due mainly to what's called persistence of vision, the way your eye and brain works. If the spot's moving very fast across the screen, the eye just sees a continuous line. Now, the setting we're using is 5 milliseconds per division. That means each horizontal division, there are 6 of them across the screen, each horizontal division represents a time of 5 milliseconds, just like having a graph with X showing the time values, like a time axis across. Take a careful look at this. There are a couple of questions for you to answer. First, how long is one sweep? A sweep is one movement of the spot from the left all the way to the right. And the second question is, how many sweeps are there per second? Pause the video, see if you can work out the answer to those questions. Okay, let's do it. How long is one sweep? Well, there are 6 divisions across, so the spot has moved across 6 divisions. Each division is 5 milliseconds because that's a time-based setting. That means the time it's taken, 6 divisions times 5 milliseconds per division, 30 milliseconds, 0.03 seconds. How many sweeps are there per second? Well, how many 30 milliseconds are there in a second? We've just got to divide 1 second by 0.03, and to 2 significant figures, it's 33. So each sweep occurs and instantly the next sweep occurs, and that happens 33 times each second, giving the illusion of a continuous line, but it's actually the spot moving across very quickly. Now we get to the clever bit. Suppose we have an alternating voltage represented by this symbol. We apply that to our Y input. That will make the spot move up and down. But while that's happening, let's suppose we've got the time base on, set to 10 milliseconds per division, and the spot is being moved across the screen while it is moving up and down. We've got 2 processes occurring together. The result is this pattern, very familiar pattern, sine wave. It's because the voltage is moving the spot up and down while the time base is simultaneously sweeping it across the screen. And that process is happening over and over again, and you see a continuous line. Now, look at the settings we're using and see if you can answer these questions. What is the period? That means the time for one full cycle. What is the frequency of the vibrations? How many cycles or vibrations are there per second? What is the peak voltage? What is the maximum voltage of this alternating supply? Pause the video, see if you can answer those questions. Here are some answers. First of all, let's get the time period, the period. We could measure one period on the screen directly. It's slightly more accurate to measure as many periods as you can and divide by the number of periods. We've got 2 complete periods here, haven't we? From the beginning, that's 1, and there's the second period up to this point. And that's about 5.6 divisions. 1, 2, 3, 4, 5.6. So we've got 2 periods is 5.6 divisions. Each division is 10 milliseconds. So the period is 5.6 divisions times 10 milliseconds. 56 milliseconds, but that's for 2 complete oscillations. So if we divide by 2, we get the time for 1 oscillation, which is the period. It's 28 milliseconds. To find the frequency, it's 1 over the period. 1 over 28 milliseconds is 28 times 10 to the minus 3 seconds, comes to 2 significant figures to 36 hertz, 36 cycles per second in old-fashioned terminology, 36 hertz. How about the peak voltage? Well, we measure from the 0 position, which is the middle, to the maximum. What's the height of the graph? It's 1.3 divisions. And each division is 2 volts on the y-axis because the setting is 2 volts per division. The peak voltage is 1.3 times 2. It's 2.6 volts. What do you think would happen if the time base would change from 10 milliseconds per division to 20 milliseconds per division? Pause the video, have a think. The answer is this. The pattern would get compressed. If you think about it, it makes sense because each horizontal division represents a longer time. And a final question for you. What happens to the display if you actually turn the time base to off? Pause and think. And we would just see a vertical line. The alternating voltage would be making the spot move up and down rapidly. But because the time base is off, the spot is not being moved left to right. It's just remaining in the central left-right position. We see a continuous vertical line. Quite a good way to measure the peak voltage actually, by measuring the height of the line. Okay, thanks for watching.